Hey everyone, and welcome to the class. I am absolutely thrilled you're tuning in today because we have a really fantastic explainer lined up for you. We're going to put on our architect hats and dive into a highly interactive lesson on how basic, simple geometry actually constructs the majestic, towering world around us. I mean, have you ever looked at a massive skyscraper or some ancient tomb and wondered how humans actually figured out how to put it together? Well, today we're going to strip all of that complexity away. We are going to look at the hidden shapes hiding right in plain sight. Okay, let's take a super quick look at today's lesson plan. We'll kick things off with our welcome, then move right into modeling giant monuments down to basic blocks. After that, we'll unfold the blueprints by looking at 2D nets, run a quick structural stress test with angles, and finally, I'll be sending you off with a little bit of geometric homework. Let's get started. All right, part 1, welcome to architecture class. So, picture this. You're on a vibrant summer trip to Delhi, a city just packed to the brim with massive, intimidating historical monuments. You know, places like the India Gate, Sunset Pond, all those ancient tombs. When you stand in front of them, they seem impossibly complex, right? But let's simplify things for a second. Notice our student here, Diksha. Inspired by her trip, she decided to just build a model of the India Gate right there on her floor. She isn't using intricate architectural tools, she's literally just using simple wooden geometric blocks. A couple of rectangular prisms for the pillars, a flat slab for the roof. And the crazy thing is, just like Diksha, professional architects use these exact same basic 3D shapes to dream up and build real-world masterpieces. Moving right along to part 2, modeling monuments with blocks. Let's do a quick mental exercise and actually apply this block thinking to a real-world heritage site. I want you to think like a master builder for a second here. Imagine you're tasked with creating a model of the famous Qutb Minar in Delhi. What fundamental shape would you stack up to create a massive, towering 5-story heritage site? Think about its round, tapering profile. Well, if you guessed cylinders, or maybe tapering cones, you're spot on. The Qutb Minar, which, fun fact, happens to be the world's tallest building made entirely of bricks, is essentially just a series of stacked, slightly tapering cylindrical shapes. By breaking it down into these exact shapes, we can really begin to wrap our heads around how it was engineered to reach such incredible heights. Look at these side-by-side examples. Whether it's the cylindrical base of a traditional clay hut with a conical thatched roof, or the massive boxy cuboids of a modern city street, it's really all just basic geometry. The environments themselves look completely different, right? One is very rural and traditional, the other is super urban and modern. But the mathematical language of shapes used to construct them, exactly the same. And here's the absolutely crucial point. Materials might evolve, but the geometry doesn't. Back in the day, people built with clay bricks, stone blocks, or carved wood. Today, we might use concrete or hollow blocks. But notice how the rectangular prism shape of your common everyday brick has remained virtually unchanged. That blocky geometry is just the universal foundation of construction. Okay, part 3, unfolding the blueprints. To truly understand a 3D building, or really any 3D shape, we first have to figure out how to flatten it out into 2D. Imagine taking a building, or to make it easier, a simple cardboard box, and carefully peeling it apart right along its edges. You're basically unfolding the 3D object to see the completely flat surfaces underneath. When you lay the whole thing completely flat, it looks like this. This flat 2D layout is called a net. You can kind of think of a net as the ultimate blueprint. If you were to cut this shape out of paper and fold it right along those dotted lines, boom, the 3D structure pops right back into existence. Literally every single structure around us, from a tiny little box to a massive skyscraper, can theoretically be unfolded into a net. Let's classify a few of these 3D shapes on our virtual chalkboard for a second. There are 2 major families of shapes we constantly see in architecture: prisms and pyramids. Prisms are built with common rectangular faces all along their sides, and they have consistent flat tops and bottoms. Pyramids, on the flip side, rely heavily on triangular faces that all angle upward and meet together at a single sharp point. You can clearly see the striking visual difference here. Take a look at the blue prisms. They are boxy, stable, and flat on top, whether they have a triangular base or a hexagonal one. Contrast that with the pink pyramids, where all the triangular sides slope up to converge at one single vertex at the top. It's a totally different architectural vibe. All right, time for a lightning round recap on the anatomy of these things. If we take a standard building block like a perfect cube, the math is always beautifully consistent. It will always have exactly 6 flat faces, it'll have 12 straight edges right where those faces meet, and 8 sharp corners. If you know these basic properties, you can calculate exactly how many blocks you need to build pretty much anything. Which brings us to Part 4, Angles and Building Strength. Okay, class, for our final core lesson today, we're going to run a bit of a structural stress test. Because as it turns out, it's not just the shapes that matter, it's the actual angles inside them that dictate a building's ultimate strength. When you look closely at the world around you, at windows, the edges of books, or building foundations, you'll see right angles literally everywhere. That perfect 90-degree L shape is heavily relied upon to hold things straight and true. But here's the question. Are they actually the strongest angle to use in a structure? Let's test it out. Imagine you build a really simple rectangular frame out of, say, drinking straws and little balls of clay at the corners. So it has 4 perfect right angles. Now, what happens if the wind blows, or if you take your finger and just gently push hard against one of the top sides of that straw rectangle? Well, no surprise, the rectangle completely collapses. It goes totally squishy. When pushed, those perfect right angles in the clay immediately bend, shifting into sharper acute angles and much wider obtuse angles. The whole shape fundamentally changes. But if you make a triangle out of straws and clay and push the side, it absolutely does not budge. It strictly holds its original shape. And honestly, this brings us to the absolute golden rule of structural architecture, pulled directly from our source text. The triangle is the most rigid shape, as it does not change its shape when pushed. This is exactly why you see triangles hiding in the trusses of your roof or the girders of massive steel bridges. It's just the ultimate unyielding shape. Finally, Part 5, your geometric homework. As our architecture class wraps up for today, it is time to take these lessons off the chalkboard and out into the real world. We've talked a ton about perfect rectangles and rigid triangles, but think about how standard shapes with perfect right angles are fundamentally different from, say, slanted, non-rectangular four-sided shapes like this one. If you build with shapes that don't lock their angles in rigidly, your structure is going to act very, very differently under pressure. So here is your actual homework assignment for today. I want you to take a moment right now and look around whatever room you're sitting in. Identify the fundamental shapes acting as the nets, the prisms, and the pillars of your environment. Take a look at the corners holding up your ceiling and ask yourself, based on the geometry we uncovered today, is your room rigid enough to stand the test of time? Keep looking for those hidden shapes out there, everyone, and keep learning. Catch you next time.